So I thought that I would talk about some new and emerging developments in solar energy. So before I talk about new and emerging developments, I just wanted to give you some background. I met with a number of people today, and I see that some of you are not only familiar, you are way ahead in certain things. But there are others who may not be that familiar with these things. So I thought I should put some background here that solar energy can potentially play a very important role in most of our energy needs in daily life. That includes heating, cooling, daylighting, building type of applications, electricity production, whether we have photovoltaics or solar thermal, fuel production, transportation, and desalination, cooking, and many other applications. Now, you know that in 1 hour seminar I won't be able to cover all of these, but they're all important in some ways. As I found out last week, I was in India for a conference. They asked me to give a keynote lecture, and their focus there was rural applications. Then in some areas of the world, desalination is extremely important. Okay. So later on, when we have questions and answers, we can discuss any of those, and if I don't know the answer, I'll tell you so. And if that's an area where I've done some work and I understand some things, I'll be happy to answer. So with that background, just start with photovoltaics. That's an area where so many developments have taken place over the last few years. And costs kept coming down, but somehow something else needed to happen to bring the costs way down, and there were two things that happened. One was what we call the building integrated applications, especially the involvement of architects in this area. You know, we engineers kept working on the development of photovoltaic cells, improving the efficiencies, reducing the cost, but when these architects got involved, then the companies started producing kinds of cells and kinds of panels that could be integrated in buildings in ways that they looked attractive also, which increased the market, and therefore a lot more companies got involved in it. And finally, when Europeans got more involved, especially Germany, by way of feed-in tariff, that increased the market so much that the photovoltaic manufacturing and photovoltaic deployment increased tremendously. As you can see, the way it has increased, this data is only up to 2010, but 2011 data is even better. And so the average annual increase from 2000 to 2010 is 48% per year, unheard of in any other energy technologies. In fact, 2009 to 2010 was 129%. Now, that's not the only way we can convert sunlight to electricity. We have another way, which is indirect conversion. That is, you convert sunlight to heat and then heat to power, like in any thermal power plant. So I'm just showing a couple of examples here. This is one which is called the central receiver or power tower type of concept, where reflectors reflect onto a central receiver and you can produce very high temperatures. Here's another example which has long rows of parabolic troughs, and again you concentrate sunlight on the focal line of the parabolic trough, and you heat a fluid, and then you go through the normal thermal power cycle. Or you can have parabolic dishes. So any of these methods of concentration can be used to convert sunlight to heat at a high temperature, and then go through your thermodynamic power cycles. As early as 1990, 354 megawatt of this capacity existed in California. By the way, that plant, which was built in stages, and I think the last stage was finished in 1989 or 1990, is still operating. The owner of that plant right now is Florida Power and Light. They happened to buy it, and so they learned from it, and based on that, they built another plant in Florida, and now they're building in Spain and other parts of the world. However, at that point, the development stopped. If we have time later on, I'll tell you why it stopped, but most recently, there's a resurgence of interest in this technology in Spain, US, India, China, and more than 3,000 megawatts is under construction right now at this point. The main interest comes from electrical utilities, which are interested in large-scale central power plants. And because this is where you can integrate solar power with backup fuels, you can include thermal storage, and that makes it possible for them to have power whenever they need it, so they have more interest in this technology. Now, photovoltaic costs, in the 70s, it was about $100 a watt. Then came down to about $30 a watt. In 2003, it was down to $3 a watt. I remember that I attended a conference in the late 70s where somebody said that one day photovoltaic panels will cost $1 a watt, and everybody in the audience laughed at that. But that actually came true in 2010, and right now the cost is less than $1 a watt. In fact, a company that I advise, they got a bid from a German company at 65 cents a watt, panels delivered to site where they are going to install those panels. Okay. However, these are just the panel costs. The balance of the system adds another couple of dollars to it. Okay. So in these technologies, we're moving in the right direction. The efficiencies are going up, the costs are coming down. However, in photovoltaics, based on the current concepts, we're reaching the limits of cost reduction. Although there are many areas of research, people are looking into materials that are not rare, people are looking into materials that are not toxic, so that solar cells can be made in a sustainable way for a long period of time. But in terms of cost, there's not a whole lot more. There will be some reductions, but not a whole lot. There will be reductions, though, in the balance of the system. Okay? Solar thermal power costs have remained pretty much stagnant since 1990. Okay? At that time, I heard the cost projection of about $3,500 a watt, a kilowatt. Today also, we hear the same cost. Okay? And energy storage is sort of missing in all of these cost calculations. So with this in the background, I thought that I would tell you some new and exciting concepts and developments based on innovations and scientific R&D. Now, they cover a vast area. It's because I picked those three where our group has been working in some way. But at the same time, as I said, at the end of it, you want to focus on one of them or you want to focus on entirely different, we'll be happy to discuss. So these examples that I will talk very briefly. Now, I do want to say that I'm not going to go deep into any of those in my presentation. The reason is that in some of those a few of you may already be working in it, and you may know a lot, but there are others who may not know anything about it. So I've kept it at a level where people who don't have that background can still understand it. So first, beyond photovoltaics, new concepts in direct energy conversion. Then new concepts in solar thermal power. And finally, I thought I'd put one in environmental application of solar energy, which is the photocatalytic oxidation for disinfection and environmental cleanup. Okay, starting with the antenna or the new direct energy conversion, that's based on nanoscale antenna to convert solar energy to electricity. And the difference is this, that the conventional PV is based on band gap, so there's a limitation. We're trying to continue to improve efficiency based on multi-junction cells and so on, but still there's a limitation. So a different concept was proposed in 1968, which was based on the wave nature of light, and that was to use antenna. In fact, Professor Bailey and Fletcher, who was at NASA at that time, they got their patent in 1973. However, in their patent and in their later development, they kept looking at antennas of insects and those kinds of concepts, but in terms of actually fabricating something, they did not have the technologies that could work for them. So the background is antennas are conventionally used for RF emission and reception. The proposed concept would use much higher frequencies. And at a frequency of 2.545 gigahertz, the concept has been demonstrated at over 80% efficiency, and it requires an antenna and a rectifier combination. So that's why the name is known as rectenna. Now, here's the thing, that even though it has been demonstrated at such a high efficiency at 2.45 gigahertz, when we want to convert sunlight, we're talking about hundreds of terahertz. And so it does present problem, and I'm not going to tell you that the technology in this area will be developed next year or next 5 years. It may be 10 years from now, or it may be even longer. It all depends on how many people get involved in research in this area and how much research they do. So here's the problem, that FM broadcast wavelength is in meters. Therefore, your antenna size in meters. And your UV visible, the wavelength is in microns or nanoscale or microscale. Okay? So your antenna size has to be that small. And in fact, the rectifier size even becomes even smaller. And so that's where the holdup is. In the past, there was we did not have the technologies, and now with the advent of nanotechnologies, I think this concept needs to be revisited. Okay. So here is some dimensions. I don't know whether people in the back can read, but the first one I've written 94 gigahertz. Now that's a frequency that is of interest to the Department of Defense, so I won't say much about it. But they have a lot of interest in that. And then on the right-hand side, we have 300 terahertz to 450 terahertz. Now, this is the visible and near infrared frequencies, and that's where most of the sunlight is. And but because we cannot jump to that right away, we felt that maybe we should work somewhere in between, and that's at 30 terahertz, which gives a wavelength of 10 micron, and that's far infrared. So at that, for the antenna, the size is in microns, and for the diode, the size is even smaller. And if we go to visible and infrared, near infrared, you see the sizes become even smaller. Okay. So here is a concept that we are following. Where we would absorb sunlight and re-emit it in the infrared. And that would use plasmonic emitters. So here you would have the plasmonic emitters, because then we can see what frequency or what wavelength we need. So we have emission, and we have the antenna and diode designed for that frequency. So with that concept, if we can convert infrared, that is far infrared, to electricity, and we can show that this concept works, then we can continue to work at higher and higher frequencies. So that's the whole idea. Now, as far as making antennas of that size, as I told you that with nanotechnologies, it's not a big problem. In fact, Idaho National Engineering Lab, a group over there, and a company that they were working with in Boston, they did a press conference where they showed a flexible substrate on which they had printed these antennas, millions of antennas. But they also agreed with me when I called them that the problem is really not antenna, the problem is the diode, because each antenna has to be integrated with a diode. So the diode concepts that work at lower frequencies would not work at frequencies that high. So you have to go to other concepts. We started looking into MIM diode and found some success, although this is not, the characteristics are asymmetric, but it's not that good a rectification. Then we started looking into polymer-based rectification, where we can use the self-assembled monolayers for actually for the insulator layer of MIM diodes. And we found peak rectification ratio of 150 to 200. So that gives us some hope that we are moving in the right direction. Okay. Ultimately, though, what I foresee is that you will have biological antenna and biological diodes. Okay. The advantage in this concept, although it still needs to be shown that we have converted that at a certain efficiency from infrared or from visible light, even though it's been shown in the radio frequency range, that the biological would be based on work that has already gone on in terms of single-cell algae that people are working on. Eventually, that's where the development will go. So if you can do that, then you could do ambient radiation. In other words, it will not be just the visible light during the daytime, but radiation at any other time also that could be converted, and you could then start foreseeing that you could have buildings which are covered with these biologically grown antennas that are converting ambient radiation to electricity at all times. Okay. So that's one of the concepts. Now, another thing I said was solar thermal power. And here's the problem with solar thermal power, that when you look at the costs, solar thermal power costs are more than 2 times the cost for coal power, and coal power is the biggest, or coal is the biggest source for generating power in the world right now. Okay. We can talk all about environmental benefits, why solar power should be preferred even though it's more expensive, but we also know that in practice that will not happen. So we will have to reduce the capital costs of solar thermal power by 50%, at least 50%. And so the question is, what do we expect to see in the future, or what should we do that will reduce these costs? I'm involved in a small startup company, co-founded, and they're building a demonstration 1 megawatt power plant where they have shown that they can already reduce the cost from $3,000 a kilowatt to $2,000 a kilowatt. But that's not enough. We need to reduce it even more. So there I see the future developments that we need to work on include new thermodynamic cycles, improving the efficiency of conversion in thermodynamic cycles. This is important because in thermal power, we have been working with thermodynamic cycles like Rankine cycle that were developed more than 100 years ago. And to say that they had thought of everything 100 years ago and we can't make any improvement on that, I just don't buy that. So we can look at thermodynamic cycles, and the kinds of things that I see us working on would be the cascading cycles, which, by the way, we are already doing in combined cycle. We have a Brayton cycle and then a bottoming Rankine cycle. But you could have a number of cascading cycles. You could, right now, we only work with pure working fluids like steam. You could work with mixed working fluids. Right now, we mostly work with subcritical cycles. We could do the supercritical cycles. So these are some of the ideas, and I'll talk a little bit more about these. In addition, and this is important for solar thermal power, that thermal energy storage can be implemented even now, and it's being implemented in the plants that are being built in Spain. But we can reduce the cost of those, cost of thermal energy storage by as much as 50 to 80%. Okay? So I'll talk a little more about that later on. But right now, let me tell you this. All of the thermal power plants and all of the solar thermal power plants are based on pure working fluids or single working fluids. The problem with single working fluid is that that fluid boils at a constant temperature when the pressure is constant. And it gives us what we call a pinch point problem. That is that because the temperature of the fluid that is being heated is less than the temperature of fluid that's giving the heat to it, you cannot violate that condition. That means that there is heat left in the heat source fluid that you cannot utilize, and you cannot heat your fluid that you're heating to the temperature that you could. If you could heat a fluid, let's say in this line, you can go to much higher temperature, therefore utilize your heat source much better. Okay. That's something that we did not need to think about before, we did not need to do, but now it makes a lot of sense, because we have to see in the thermodynamic cycles, can we improve the efficiency by 5%? Well, forget about 5. Can we improve the efficiency by 1%? Because when you're building a 100 megawatt power plant, 1% improvement in efficiency in terms of money is big improvement. Okay. So we need to look at everything there, and this is one of the ideas where the question is, how can we do that? Well, we can do it by multi-pressure boiling, we can do it by supercritical boiling, and we can do it by multi-component mixtures. Okay. So we started looking at multi-component mixtures, and now we're looking at supercritical boiling. In terms of multi-component mixtures, these are some examples. You could use mixed hydrocarbons such as isobutane, pentane, hexane. This is for lower temperature power cycles. You could use ammonia water, and there was a cycle that was proposed by Alexander Kalina, which is called Kalina cycle, that's based on ammonia water mixture. Okay? Because when you mix the fluid, as the fluid boils, the temperature doesn't remain constant. The composition of the fluid changes, therefore its boiling temperature changes, and you utilize your source much better. Same thing in condensation. When you condense that, because the composition changes as one component starts condensing, therefore the temperature changes, and therefore you utilize the heat sink much better than you would otherwise. Okay. So we followed this process of multi-component mixtures and actually came up with a new cycle. And this cycle, actually in the literature, it's named after me. It's the Goswami combined power cooling cycle. Okay. In this, you would boil that multi-component mixture, and you would get maybe mostly one component. And we started with ammonia water in this case, so I'll give you that as an example. But its cycle is now extended to a number of other fluids. So when you're boiling a mixture of ammonia and water, ammonia will boil first. And therefore, what you have here in the superheater is mostly ammonia, very small amount of water. Okay. And so now you expand that in the turbine and you produce power. The rest of the water that did not boil off now comes back, and you can remove some of the heat from it, and then it gets mixed with ammonia. Ammonia can be condensed by absorption in water. So it removes a constraint from ammonia, and that constraint is normally when you bring this fluid out of the turbine, its temperature has to be above ambient so that you can transfer heat to the ambient, whether it's ambient water or ambient air. Now, because we can condense ammonia by absorbing in water, you don't have that constraint. That means you can expand ammonia in the turbine to much lower pressures, therefore much lower temperatures. So you could get ammonia out at a temperature as low as 0 degrees. So now you can first remove some refrigeration from that ammonia and then bring it to the absorber where you condense it. Now, we're not violating any laws there, thermodynamic laws, because you still have to transfer heat to the ambient. And you can only transfer heat from higher temperature to lower temperature. So what happens when you absorb ammonia and water, ammonia condenses, gives up its heat of condensation, and this temperature goes above ambient. That's when you transfer the heat. Okay. And so this way, this cycle works. As an example, under these conditions, and at the time when I developed this cycle, I was really thinking about low temperature applications. And so I picked these temperatures and found that we could get a work output of this much, refrigeration out this much, with total heat input this much. That gives us a cycle efficiency of about 20%. As a comparison, the ideal Carnot efficiency is 31.7%, and Rankine cycle efficiency is 16%. So we have improved almost 25% over the Rankine cycle efficiency, but we have also produced refrigeration in addition to power. Now, at some places you may not need refrigeration, but the cycle can be tweaked to produce all power, all refrigeration, or a mixture of power and refrigeration. Okay? So that's why it's called the combined power and cooling cycle. More recently, we are looking into much higher temperatures. The reason is that as far as solar thermal power is concerned, we're all moving towards higher temperatures. As you know, as you go to higher temperatures, the Carnot efficiency is higher. And therefore, if you can improve the efficiency of conversion without increasing the cost much, you reduce the cost. So let's say that you can go to temperature of 1000 degrees C. That presents problem as to what working fluids you will use at that temperature, or even lower than that, maybe 800 degrees C. So supercritical CO2 is one of those fluids that can be used. And in this case, the only thing is that to condense CO2 in normal thermodynamic cycle, if it's using steam, for example, then you would condense steam to water. Okay. In this case, the critical temperature of CO2 is very low. So only in very cold climates that you'll be able to condense it. But if you bring it close to supercritical condition, or the critical point, at that point the density is extremely high. And therefore, it's not like compressing liquid, but it's not much far from that also. And therefore, this cycle can give you very high efficiencies. In fact, for a temperature of about 750 or 800 degrees C, the efficiency is more than 50%. So compare that with the present solar thermal power plants, which are using steam cycle with an efficiency of somewhere between 30 to 35%. This is a major improvement, and therefore the additional cost reduction that we need will come just from that. Now, that's about the thermodynamic cycles. About the storage, in solar thermal power plants, now, some people think there's a competition between photovoltaics and solar thermal power. I don't think there's a competition. There are niche markets for photovoltaics, there are niche markets for solar thermal power. In large-scale power, you want to ensure that this power plant doesn't operate just during daylight hours, that it operates in non-solar hours also. And you want to ensure that you can provide power at all times, at least all times when it's needed. So that means if you need to use a backup fuel, that you can use that. And both of these can be done in solar thermal power. Solar thermal power, by the way, is also called concentrating solar power, or CSP. Now we have concentrating PV, and so some people say, well, concentrating solar power is concentrating PV also. But the acronym CSP was used for concentrating solar thermal power, and we still use that. Okay. So this shows a schematic of a concentrating solar power plant where you have thermal storage over here. And in this case, whether you use a molten salt, or in most of the power plants right now, we use synthetic oil. So you use that for storage, you just heat it up. And molten salt, the same thing, you heat it up. But you've got to have two tanks. One where you have the hot salt or hot oil, and the other where you have cold oil. Okay. Because you don't want the hot and cold to mix in one tank, because that will bring the temperature down, and so you will not be able to use it that well. Okay. So this is the type of thermal storage we have. The cost right now in Europe, the companies are quoting costs of about $80 per kilowatt hour thermal. That is the capital cost of thermal storage. In US, I've heard numbers of about $40 a kilowatt hour thermal. Now, how does thermal storage help? In solar thermal power, you have invested in the beginning in two parts. One is called the solar field, where you have the solar reflectors and the tower or the tube at the focal line of parabolic troughs, where you have the working fluid. So that's called the solar field. The other part is the power block, where you use the turbine and the condenser and the pumps and heat exchangers. Okay. So you have made investment in both. The power block is only being used during the solar hours. If you have thermal storage, you can utilize that investment for later hours also. And therefore, the effect of that is, even though with storage the capital cost goes up, the levelized cost of energy, as you can see over here, the levelized cost of energy actually goes down depending on the solar multiple and the number of hours of thermal energy storage. So this is if the cost of solar energy or solar plant is the same as we have today. Okay. If we reduce that cost to $2,000 a kilowatt, as I said, that this company that I'm advising, they now see that they can make a solar thermal power plant with central receiver at that cost, then your levelized costs come down to actually below 10 cents a kilowatt hour. Okay. Now, if with the help of our thermodynamic cycles that I talked about, we can bring this cost down further to $1,500 a kilowatt, then we can compete with coal power. Okay. So that gives us a roadmap towards competing with the conventional power. Okay, now I talked about this two-tank storage. You can actually use a single tank also, as long as you can maintain the thermal stratification within the tank. That means the top side of the tank remains hot and the bottom remains cold. That is, you don't allow the thermal storage medium to mix. So there are ways to do that, and I will just give you one example of how we are doing that. Okay. So we decided to actually use phase change materials and make spherical capsules out of phase change materials, and that same tank that would be used for oil storage or molten salt storage would just dump these capsules in there. Okay. Now these capsules remain in place, therefore you maintain your thermal stratification. So you need only one tank, and so we expect that we will be able to reduce the system cost from $80 that's being quoted in Europe to less than $10 a kilowatt hour thermal. Okay. And so with the two developments of thermal storage and the thermodynamic cycles, I think we can then compete at large scale with the conventional power. Okay. So here I just wanted to show a few examples of what we have done with these capsules. These are the material, the phase change material we use is salt, and salts are very cheap. In this case, up to about 300 degrees C, we're just encapsulating them in a polymer. When we go to higher temperatures, we add a layer of metal on top of it. And actually these capsules because this was under the Department of Energy program, and our goal was in the first phase to make sure that these capsules go for hundreds of thermal cycles, heating and cooling, without any degradation in the performance. They've actually gone through 500 thermal cycles. Our objective is to take them to 10,000 cycles, which is what they would expect to see in their normal life. Then we went to higher temperatures, and we made, then the encapsulation material is ceramic at that point. And this is actually sodium silicate. And what we did after taking it through cycles, we actually cut it to see what happens inside. And we just wanted to be sure that the salt is not diffusing through the first layer into the encapsulation material. So now I come to the third application of solar energy. This is solar photocatalytic detoxification and disinfection. As I said in the beginning, and Professor Wagner said that my background is solar thermal, but over the past 35 years, I've gotten interested in many different applications. And in doing that, I get to work with very interesting people, and I learn from them. So in this case, I learned not only some chemistry, but I also learned microbiology and disinfection. So it started as an innovative application of sunlight to clean up contaminated water and industrial wastewater. Okay? And as we developed the technology, we found applications that were much beyond what we had originally imagined. And in many cases, this technology works where all others fail. And this is, the next is just a news clip that sort of explains in layman's terms what this technology is.
It's a matter of chemistry that's well known to anyone who does laundry.
If you leave colored fabrics out in the sun for too long, they're color faded. That's because the ultraviolet part of the sunlight has acted on that color molecule and breaks it up.
Engineers at the University of Florida have been applying this principle to the process of cleaning up groundwater that's been contaminated with organic chemicals like dioxin or PCBs.
We put a catalyst in water and expose it to the sunlight, that is the ultraviolet part of the sunlight. As the ultraviolet photons are absorbed, they cause a chemical reaction which breaks up chemical bonds.
The catalyst is titanium oxide, an ingredient in white toothpaste and other products.
It's used as a pigment in paints, it's used as food additive and a number of things that we use. And it's available abundantly. It's probably the second most abundant material available in the world after salt.
And it successfully cleaned up water in the lab.
The darkest color is the water we put in the reactor, then we got the next color as it went through, and finally this color is
Over at Photovoltaic base in western Florida, Professor Goswami's graduate students have taken the process from the lab to test it in an actual cleanup site.
The site was previously used for a what they call POL, petroleum oil lubricant storage area.
Over the years, leaks from tanks and spills during fuel transfers have resulted in contamination of the groundwater. It's an ideal area to put the process to the test. Groundwater mixed with titanium oxide is pumped through narrow tubes in the solar reactor.
The goal is complete destruction, taking the hydrocarbons down to carbon dioxide and water. We do not want to create anything more hazardous than what we started with in the first place, which is possible when we start having oxidized with concrete. We're taking great care to prevent that here.
Professor Goswami has great confidence in the process.
In fact, we've not seen any organic chemicals, or we've not tested any on which the process was not going.
If he's right, this may be the beginning of cheap and easy way to clean groundwater in some parts of the world.
obviously the solar aspect is not going to be applicable to everywhere. If you go up to the Maine, it's going to be hard to run a solar powered unit year-round.
For now, testing continues in the Sunshine State. Scott Gable, CNN, Future Watch.
So that gives a layman's explanation. And of course, we continued to work in it and found that we could not only clean up groundwater, but industrial wastewater from pharmaceutical companies. And then we got into disinfection of water and finally disinfection of indoor air. It turned out that the application really did not become commercial as we thought it would. Part of the reason was, the main reason was, that cleaning up industrial wastewater or cleaning up contaminated groundwater was all based on regulation. If the regulation did not require somebody to clean up, they did not need to. There was a company, a pharmaceutical company, that had a plant in Puerto Rico which was making a drug called 5-fluorouracil, which is a cancer drug. And they had tried all the methods that they could to clean up the wastewater from that plant, and they could bring the COD down to a certain level but not below that. Then they approached us, and one student did master's thesis and showed that with the photocatalytic process, we could clean it up to the point that they could reuse that water. And when I presented the results, I asked the vice president for that company, would you now use this process? The answer was no. He said, it's good to know we have a process that we can use when we have to, but right now we're not required to. But on the other hand, when we applied this to disinfection of air, this process became commercial faster than we wanted to. That was because it wasn't based on regulation, it was based on real need of people. And so you again watch a news clip here.
600 people used to work in the Central Florida courthouse, but now the doors are closed, the hall is empty, and these are the only workers allowed inside. The Polk County Courthouse is a sick building.
There were also problems with the air conditioning, that it wouldn't properly be notified the air and humidity was over too high, and that caused mold and nobody was wrong with all that.
Bacteria buildup and poor ventilation are typical in sick buildings. Some of the workers here developed health problems ranging from runny noses to permanent crippling lung conditions. The entire building was shut down. Everything inside is being replaced. The cost to taxpayers, $37 million.
The hard part for the citizens of Polk County, however, is they are paying for it twice in a way, and that's very unfortunate.
The money to fix this building is already spent.
And the future learns velocity.
But a University of Florida professor has a new solution that could save millions in the future. An air filter coated with a common chemical is used with ultraviolet light and installed in an air duct. The system kills most bacteria as the air filters through the trap. Researchers say it would cost a fraction of what it would now take to fix the thousands of sick buildings across the country.
Instead of replacing the whole duct system, you simply replace the filter system, which will be much cheaper than replacing the system.
So the new process comes too late for this courthouse. Now these are the judges who will rule on when workers can return. In Polk County, I'm Karen Brunel reporting.
So, as I said, that as soon as the news went out, everybody wanted to buy a unit. And in the university, we were not the people who could sell units. Some company had to be formed, which was formed, and eventually that company got sold to a much larger air conditioning company, which is now selling these products and anybody can buy. And at the moment, though, there are companies all over the world which are licensing that technology from the University of Florida so they can sell it in India and China and Asia and other places. Then we found that this technology can actually be used as a defense against bioterrorism. And there, this is what you see is Bacillus subtilis, which is sort of a close cousin of Bacillus anthracis, which is anthrax. And with the photocatalytic technology, now this is how it looks before you shine the light on it, and after you shine the light, as you see that it is literally evaporating, that is being converted to carbon dioxide and water, okay, so that it can be used for defense against bioterrorism. The ongoing research in this is to increase the rate of destruction so that it can indeed be used as a defense against bioterrorism, and to extend the useful wavelength range to utilize the complete visible spectrum instead of just utilizing the UV spectrum. But as I said, then this technology has become very popular, and we started seeing other things in the market. This is from Japan. It says self-disinfecting medical catheter. Pilkington is a very large glass company that's advertising self-cleaning glass. And then we saw an Australian company saying that you can have self-cleaning clothes. All you have to do is shine some light on those clothes. And then we saw that in the popular science. And finally, this I think goes too far. So people have their imagination. Now you've seen some examples of the things that you can do with sunlight. There are many applications, and of course, sunlight or solar energy is what we need for food. We also need it for our energy and the environment, because this is what gives us the natural solution. Thank you.
So if you have questions, please raise your hand and we'll come around with the microphone.
So at the beginning, you were talking about antennas to capture energy, and I couldn't help but think about possible applications in terms of transmission of energy by basically controlled microwave radiation. Is that something you are working on, or is that the Defense Department part?
That's actually, that was proposed. There was the A.D. Little company, right? Arthur D. Little company from Boston. Their chairman at one time was the big proponent of converting sunlight to electricity in space, converting it to microwaves, and then beaming microwaves to Earth. But there are problems with it. As you can see, that if you're beaming a concentrated beam of microwaves, that how that could be misused. And therefore, I doubt that anybody will do that, but it was proposed. But maybe in shorter distances, it could be done.
Thank you for your presentation. I have a question about residential use of solar power. From your presentation, the cost of the solar panels have dropped significantly since President Carter put solar panels on the White House. So that would make me think that residential solar power is more cost competitive today with the conventional fuels of oil and gas. Number one, is that true? And if so, do you have any other comments on residential use of solar energy?
In many parts of the world, you're right that the photovoltaic panels or the system cost would be less than the alternative, which would be the conventional power. Because in those parts of the world, people are using diesel to produce power. The cost has come down. The system, we bought a new house in Tampa, and last year we got a photovoltaic system for that house, a 5 kilowatt system that cost us about $3.50 a watt, which is much less than I could ever imagine. And right now that cost is less than $3 a watt. So the costs are coming down. Panel cost is already low. It's the balance of the system where somebody asked me earlier, what are the areas where we could make an impact? And I think balance of the system is one area where, there are a number of things in there. And so that involves multiple disciplines, not just electrical engineering, but there are other engineering areas or science areas that could be involved. But you're right that the costs are coming down to a point where, in my case, I thought it did not make sense for me not to put that photovoltaic system. And I tried to cover whatever area on that part of the roof I could, and that was little more than 5 kilowatts, which we did.
Hi, I'm just wondering about the net environmental balance of solar panels, and are these new technologies going to help with that?
I can't give you a definitive answer because I don't have all the numbers. But at one time, I'll give you parts of the answers. At one time, this was back in the 70s and 80s, where if you looked at the net energy balance, it was negative. That the amount of energy that it took to produce the panels, that you could not produce that much energy from them in their lifetime. And so there was a very famous environmental scientist, H.T. Odum, who I think in the environmental areas he's considered God, close to God. And I was on a panel with him, and he had done an analysis back in the early 80s. And he stuck with that analysis to mid-90s. He did not update it. By that time, when we were on the panel and he said that, and I said, by the way, Dr. Odum, the energy payback period for photovoltaic panels is now 5 years. And at this point, that energy payback period is less. Now, that does not answer the environmental balance. That is, what kind of environmental damage was done during the production of the panels. Now, during the lifetimes, a lot of positive benefit, because you're not generating any environmental pollutants, you're not generating any CO2. But at the end of life, what happens to those panels? So when you do it all, my guess is, but this is based not on any analysis, that the net environmental balance is much better now than it was. And so, and it's getting better. There are some materials that we use, and people who are doing research in solar cells, they're trying to find replacement for those materials so that we don't use, for example, any toxic material. We don't use any rare material. So, but that's part of the research that's going on.
Thank you for the talk. In one of your slides, you showed what appeared to be a picture of a parabolic antenna with what I believe must be a Stirling engine attached to it. And you did not discuss any of the costs of those solar thermal electrical generators, or whether any of them had integral storage, thermal storage capability. So can you address that?
Okay. I think you're referring to parabolic dish. Yep. And the Stirling engine. That's a technology that, in my view, had a lot of potential, because you could have a 25 kilowatt dish, which in a remote location where there's no grid in a village, that may be sufficient to provide them all the electricity. Or you could have 2 dishes and make 50 kilowatts and so on. But somehow, a couple of companies that got involved, they invested some money, Department of Energy invested money, and then they got out. Cummins was one of those companies. Cummins Diesel, and we thought that maybe they had interest. People say, well, maybe they just wanted to kill this technology because in all those villages right now, you're using Cummins diesel engines. And so then later on, another company got involved, Sterling Engine Systems, SES, and somehow they also did not succeed. I think the technology has a lot of potential, but because Stirling engine itself, Stirling cycle is the most efficient cycle. Theoretically, the efficiency of Stirling cycle is the same as Carnot cycle. Of course, in practice you can't get that. But so keeping that in mind, I do expect that somebody will come along who will then push for this technology.
I have a question about the direct antenna. So with a fixed antenna geometry, do you expect it to be equally effective at absorbing all the different wavelengths in the solar spectrum?
I did not get everything you said.
So with a fixed antenna geometry, because usually antennas are generally optimized for a range of frequencies, do you expect it to be equally efficient at absorbing all the different frequencies?
I just showed that as an example, and I'm not an antenna expert. And so you can have other geometries, whatever will work the best. All I wanted you to explain here is that here is a concept which is different from the concepts being followed, and it's worth looking into because for the simple reason that at certain frequency, it has been demonstrated that you can convert at extremely high efficiency, say 80% efficiency. Now, will we be able to convert infrared and visible at that efficiency? I don't know, but the potential is there. And so I would like people with that kind of background to get involved in that and come up with their own design of the antenna and the rectifier. I just showed you a little bit of the work that we have done.
Yes, thank you. You showed some comparisons with coal-fired plants. You didn't mention natural gas-fired plants, and there's been a lot of talk about how the low natural gas prices has impacted. What has been the impact of the lower natural gas price on development of the solar technologies?
Okay, well, very good question. I did not, the capital cost of natural gas-based plant is much lower than coal-fired power plant, mainly because of the combined cycle, and I've heard prices as low as $700 a kilowatt. Okay, that's the capital cost. Of course, whether it's coal or natural gas, it's not just the capital cost, it's also the fuel cost. And as you said that natural gas prices recently have come down because we have discovered a lot of natural gas. But these prices cannot remain low forever because the quantities are limited. Even though we've found more over here, but I look at it as a global situation. The prices eventually will be global prices. And so there's another presentation that I give where I look at global needs and global resources. And in there, whether it's natural gas or it's coal or oil, I look at the resource availability from the point of view of proponents of that resource. So maybe the natural gas industry, whatever they say is the amount of natural gas available, or oil industry saying how much oil is available, and then I increase it to give much more benefit of the doubt and say, well, maybe we have a lot more available because I hear the economists don't agree with geologists on this thing. Economists feel if the price of something is high enough, we will find more of it. Okay. So I do that, and then I come back with the conclusion that by 2050, at least 50% of our energy will have to come from renewable resources, a vast majority of that being solar. Even though wind and biofuels will be part of it, but they are limited also. And solar is a much bigger resource for the ultimate use. So I've sort of given answer in a roundabout way. Yes, for a short period, that can affect. But in the long run, I don't think it will.
Question about this. Question about the design of antenna and the incident light coming from solar light. Is it quite monochromatic or is it a broadband? I mean, because that determines the design of the antenna.
Right. Very good question. What we thought as a sort of interim solution was to absorb all of the sunlight and then re-emit it. And when you re-emit, it depends on the temperature. So you have a black body radiation curve. But what we are working on is on that surface which emits, we are making plasmonic emitters there, with the slots and those techniques, so that we can, even though the black body emission is very broadband, that can be, at least the band can be shortened. And so, yes, your antenna has to be then tuned to the emission that you have.
So I'd actually like to ask a question about the last part of your talk, the disinfecting and cleaning up, and specifically in terms of the process you designed where you were using UV light to disinfect or to clean up water. How many times did the water need to pass through that system, and sort of from a chemical engineering standpoint, what were the sort of the process parameters that you were using to do that?
A very good question. That really depends on the contaminants in water. And so the way we do it is we do a lab test under simulated radiation. And in that lab test, we find what we call the reaction rate constant. Okay. And based on that reaction rate constant, we do the design of the system. And in our book, this Principles of Solar Engineering, I think chapter 13 talks about that and the design process.
Okay, so let's thank Professor Goswami again. And